Welcome back, everyone. In this video, we will be finishing up the derivatives and graphs section. So in this first problem here, we're going to use something called the second derivative test. And the reason I don't like calling the other sign chart method the first derivative test, even though that's what people call it, is it doesn't seem like it's anything like it. The first and second derivative tests formally are just ways to figure out whether you have a local maximum or minimum. But the second derivative test, if you're presented the first derivative test as sort of what we did before, then you might think the second derivative test was just what we used to find concavity and points of inflection. But it's pretty different. So let's go ahead and just read it. It says, let f be a function and suppose that f prime of c equals 0. So you figured out a number where the derivative equals 0. And it says if the second derivative is negative at c, so if we evaluate the second derivative at c and we get a negative, then f has a local maximum of c, comma f of c. And we know if we want the coordinates, that's what it looks like. If you just want something like the actual local maximum value, which we'll be doing in this problem here, then you'll just give the y value. Right? And then if f prime prime of c is greater than 0, then f has a local minimum. So if the second derivative is positive, then it has a local minimum at c, comma f of c. And then the one thing that's kind of annoying about the second derivative test is if your second derivative equals 0, you can't conclude anything. It could still have a local maximum, it can still have a local minimum, it can still have neither. So I just want to take Desmos real quickly and explain this. When we talked about when we were talking about concavity at the beginning, sorry, I lost my train of thought for a second, we looked at y equals x squared. And if you do figure out where the derivative equals 0, for here, because the derivative is just 2x, then it's also at 0. And what's happening where the derivative is 0 right here is that you have a local min. And that's because the concavity here is 2, it's positive. And if you do put the negative sign on here, you still have the derivative being 0 at x equals 0, but it's a local max because the second derivative is negative 2, it's negative. So it really goes along with the first two things here. The third one is why it's so tricky is because if you just make x a bigger power, so let's say, I'll get rid of the negative, let's say we have x to the 5th. Well, this thing at this point here, if you do the derivative and set it equal to 0, you will get x equals 0. If you do the second derivative and set it equal to 0, you'll also get 0, which is inconclusive. Now we can tell from the graph that it has neither a max or a min. Well, if I just switch this now to 6, you'll get all the same information. And I encourage you, if you want to go ahead and just do the derivative, do the second derivative, see that you get x equals 0 for all of them. But at this point, it is a local min this time, even though we still have the first derivative equals 0 and the second derivative equals 0. And then if I just make this negative, pretty much the same problem happens. The first and second derivative are 0 there, but now it's a local max. So that was just a quick example of why when the first and second derivative are both 0, you can have a local min, you can have a local max, or you can have neither. The problem with the second derivative test is it won't tell you which situation you have. It'll tell you you have to do something else. And that's when we'll go to the sign chart method. So most realistic examples, when we're trying to find local mins or maxes, we don't necessarily care too much about where it's necessarily increasing, decreasing, where it's concave up, concave down. So the previous problem wouldn't be something we would want to do in that situation. We'd want to do the second derivative test. We just need to hope that the second derivative is not 0 for those problems. So let's go ahead and look through this problem. And we are told to use the second derivative test, so it must work. We're probably not going to end up with this situation. It says use the second derivative test to find the local maximum and local minimum values of f of x equals 2 plus 9x squared minus 6x cubed. Well, the second derivative test says what? Well, first thing, we need the first derivative to equal 0. So we have to solve f prime of x equals 0. Because if we don't do that, we can't even begin to plug in c to the second derivative. So what we got to do, we got to do the first derivative. Let's go ahead and do that. F prime of x, well, f of x starts with 2. The derivative of 2 is 0. The derivative of 9x squared is 18x. And then minus the derivative of 6x cubed is 18x squared. All right, so we have our derivative and we want to set it equal to 0 and solve this. Pretty much the same exact steps when we did the previous problem. We're sort of going through and finding the critical values, although we don't care about the D and E part, just where it equals 0. All right, so let's solve this. One thing about this is you can factor out an 18x because each has an 18 in common, each part, and each part has an x as well. So when we factor that 18x out, the front term, everything came out, and we just have a 1 minus, and then the second term, the 18's gone, and 1x remains, so it's just 1 minus x. And now we set our each part equal to 0 and solve it. We do have to worry about the front part here because there's an x, so we got 18x equals 0, and 1 minus x equals 0. The one on the left here, if you divide by 18, you just get x equals 0. 0 divided by anything is 0, except for 0, but that's not happening here. And then for the one on the right, if we add the x to each side, we get x equals 1. All right, now what is this telling us? This is telling us that our only possible local extrema, so local max or min, are at these two values. So only possible local max and min are at x equals 0 and x equals 1. This is sort of like the C. We just have two C values in this setup. What we want to do is do the second derivative and see whether when we plug in 0 and when we plug in 1, will we get positive, negative, or 0. So once we solve this, next, do f prime prime of x. So compute the second derivative and plug in, well, in general, we would plug in the x values we got from this step, which are 0 and 1 for our problem. But if you get 10 x values, if you get 1 x value, you plug in all of them. Okay, so f prime of x was 18x minus 18x squared. F prime prime of x, we do the derivative here. The derivative of 18x is just 18 minus the derivative of 18x squared is 36x. Now, we don't care about setting this equal to 0. So that's where this is very different. In the previous problem, we set the first derivative equal to 0. I'll just go ahead and remind you real quickly. We did this stuff in this box first. We set the derivative equal to 0. We didn't do any of this stuff in the problem we're currently doing because we don't care about where it's increasing and decreasing. We only want to care about if it's a local max or min. And the second derivative test allows us to skip a bunch of steps. So we do the second derivative and now we plug in. Okay, so let's just plug in x equals 0 first. F prime prime of 0, well, if we plug in x equals 0 here, you get 18, which is positive. And that's a very good thing. As long as it's not 0, we're happy because we can make a conclusion. Since f prime of 0 was 0, that's what we figured out in the first part. And the second part, we figured out the second derivative is positive. That means there is a local min at x equals 0. Now we really care about the y value, but like last time, I'll just hold off to do that until after we do all the derivative stuff. Okay, and then at x equals 1, we want to plug in 1 to the second derivative, f prime prime of 1, and we get 18 minus 36 times 1. Well, this is just 18 minus 36, which is negative 18, but what we care about is this is less than 0. And we kind of breathe a sigh of relief. We don't have to go through and do all that sign chart stuff because it's not 0. When the second derivative is negative, we have a local max at x equals 1. And before we go through and do the y values, which we'll just plug into the original function, I want you to go ahead and see how that works. Let's go ahead and plug in f of x to our graph and just see everything. Y equals 2 plus 9x squared minus 6x to the third. And you can scroll out here, but what you'll notice is that, and our formula should really go along with it, we have a local min, it's at x equals 0, and we have a local max at x equals 1. And that's exactly what we figured out. Now, to get the y values, we could just say, well, for the y values 2 for the min and the y values 5 for the max because the graph told us. But just to remind you, you plug it into the original to get the y values. So we know what it's supposed to be, but let's just finish up by actually completing. So now the last step is to plug in the local max. The y value will be the x value, which was 1. So the local max was at x equals 1, but we plug it into the original. Y equals f of 1, which equals 2 plus 9 times 1 squared minus 6 times 1 cubed. And hopefully that equals 5. And it does, because this is just 9. This is 6. 2 plus 9 is 11. Minus 6 is 5. And then the local min, the y value, well, the local min we had was at x equals 0, so f of 0. And we just plug in 0 to the original. And that one's probably pretty easy because these would go away and it's just the 2. But if you want to completely plug in 0, nothing wrong with that. Plugging in the 0 for these two spots will give us 0, and it's 2 for our y value, which matches up from the graph that we got. All right. So what I want to go ahead and do now is just work a couple little quick problems, just understanding and interpreting either some of the theorems we talked about in this class, lecture I mean, or just interpreting a word problem dealing with the first and second derivative. All right, so number 1 here, it says, suppose f prime prime, the second derivative, is continuous on negative infinity to infinity. All right, all that means is that all of the stuff we talked about above works because the second derivative is continuous. If we graph it, we don't have to pick up our pencil. Right, but this just makes everything work. All right, it says if f prime of negative 5 equals 0 and f prime prime of negative 5 is 1, what can you say about the local extrema of f at x equals negative 5? Well, that's actually just based on the previous problem. If the first derivative is 0, we either have a local max, we have a local min, or it's possible to have neither. But the second derivative tells us exactly what it is as long as the second derivative is not 0. And it's not, it's 1. Since f prime prime is greater than 0, it is a local min. And that's exactly the second derivative test. It's really exactly what we did before. It was the one with x equals 0. Now we're not given a formula here. We just had to use the actual information we're given. But that's the way you want to think about it. If the first derivative is 0, you have a max, you have a min. It could be neither. It's one of those flat points that we mentioned, that I showed you on Desmos. But since it's not 0, we can definitely say it's something. And because it's positive, it's a local min. If this was negative 1 or any negative number, it'd be a local max. So that's our conclusion here. We have a local minimum. Right, true or false? If the second derivative equals 0, then at x equals 3, then 3 comma f of 3 must be an inflection point. All right, this is one where we must understand that it's false. And the reason it's false is because it's necessary an inflection point must have the second derivative equal 0. But there's another condition. The second derivative must equal 0 and change sign. So it has to go from concave up to concave down, or concave down to concave up. Now this problem, it doesn't tell us anything about that. It could be an inflection point because it could change sign, but it could also not change sign. So when we answer true or false questions, we're probably getting pretty comfortable with them at this point. What we have to include all possibilities, not just the one that would make it work. So sometimes this will be true, but other times this will be false. And if it's not always true, then we have to say it's false. It's like telling the truth to someone 99% of the time and the 1% of the time you lie to them, well, can you say that you always tell them the truth? No. Even if it's pretty much always, it's not always. So it's false. All right, so the last one is related more so to a type of word problem. It says, let f of t represent the temperature at a time t where you live. Suppose at t equals 4. Now, one thing is that it doesn't matter what t means. It could be days, hours, minutes, whatever. It's not really important to this problem. And at t equals 4, you have the derivative at 4 is 3, and the second derivative is -1. Describe how the temperature is changing at t equals 4. Now, for the most part, if this problem was given to you, you'd have multiple choice. But I just want to describe it in a general way, and it would just follow along. All we really care about when we're talking about the first derivative here is whether it's increasing or decreasing. Well, if it's not 0. If it is 0, then we know it could be a max, it could be a min, it could be neither, but this is not 0. So the first derivative is positive. That means it's increasing. That means the temperature, since that's what this f is representing, at time t equals 4 is increasing. Well, we also want to add in our new thing. What does the second derivative being -1 mean? And the second derivative is just the derivative of the first derivative, so it's the rate at which the temperature is increasing this is kind of wordy and confusing, which is why it can be a little weird to read. Since we know the temperature is increasing, we have to say at the rate at which the temperature is increasing. Well, since the second derivative is negative, it's decreasing. And what we can think about this as is the temperature is going up, because that's what increasing means. So in more of like a layman's terms, the temperature is going up more slowly. So it's going up because the derivative is positive, but it's slowing how it's going up. So maybe in 1 hour, it went from 70 to 80 degrees, and then the next hour, it's going from 80 to 85. So it went up a little slower, and then it's just going to go up more and more slowly. But it's still going up. Right, so remember, that's what the second derivative tells you. It doesn't tell you increasing or decreasing. It just tells you how the derivative is changing. Now, before I sign off on this lecture, the one thing I just want to really reinforce, as I was talking about with concavity in the second derivative, is pretty much reinforcing the idea that if you're looking at a graph, it's very hard to know specifically where the concavity changes, but the idea of bending, that's really what concavity is. It's bending up or down. And then another way to interpret the second derivative is the rate of change of the first derivative, which this last problem I think does a very good job of. It tells you exactly what's happening to the derivative, but it doesn't tell you what the derivative is. And another thing I guess I should mention is that the fact that this is 3 and this is -1 only matters that it's positive and negative. This could be 300 and this could be -1 still, and I would have the same exact conclusion. This could be 1 and this could be -1,000,000. I would have the same exact conclusion. So just keep that in mind. Only matters whether it's positive or negative. I will see you in the next video.